That's true.
So I'm very happy to introduce today's speaker. He's actually a Colorado alum. He finished his PhD here in 2012.
Yes.
I think, is that right? Yeah. Before that, he did a master's degree at the University of Pennsylvania, and that's actually where we first met. He was in a class I taught at Penn. And then he did his military service in Korea, and then I was applied to do a PhD at Colorado, and I was delighted to see his application. I thought, yes, great, let's bring him here. And he did a lot of amazing work while he was here. Is one of the people who's really pushed the dependency parsing, the algorithms for dependency parsers, and also the current version of universal dependency. He contributed a lot to sort of helping people come to a consensus on dependency labels for multiple languages. And he went on from his PhD here to do a postdoc with Andrew McCallum at the University of Massachusetts. And Andrew is very well known for being very much at the cutting edge of machine learning and NLP, and his postdocs are very much sought after. And Jinho impressed Andrew so much that for every year after that, Andrew would say to me, okay, Martha, when are you going to send me another Jinho? And I did. Finally, this year, Tim O'Gorman has just started his postdoc at UMass. But if Jinho hadn't, paved the way so well for Tim, I doubt that would have happened. He now has a faculty position at Emory University, where he's continuing to contribute to a lot of different state-of-the-art approaches in natural language processing. But he's also taken on an additional challenge that's very much on the frontier of research in natural language processing today, dialogue, interactive conversation. And he's doing well enough at that of the 400 teams that applied to Amazon to be chosen to work for the Alexa Prize, he was one of the 10 that was chosen, his team at Emory. And the work that he's going to present today, which is kind of another perspective on that same work on conversation, was nominated for a Best Paper Award at Colloquium last summer. So we're delighted to have you here. We look forward to hearing what you have to say.
Thank you very much. I always introduce Martha as like my academic mom, because I was a foreign student and she has been inviting me for every Thanksgiving dinner and all these events, and I always has a deep appreciation and love for my advisors. CU is definitely one of my Boulder. So this is another thing I always keep saying to people. Boulder is my definite favorite city. I've been to many cities in the States, and Boulder is by far the best cities I've been. Best is defined very subjectively by people, but this is the, if the technology always fails you, but let me see. This is the slide I use for my defense. So by the time I left CU, Boulder was top one for many of these things. I don't know how many of these are true. So I graduated 2012, and this I'm hoping a lot of these are still true and even more. So I just want you to feel like the excitement and the usefulness of all the experience that you are getting here and all the wonderful city with the Boulder. So, and it's great to see all the old faces and new faces here too. So this happened to me like every time, and this clicker is not working, so I may have to just stand here more. The project that I'm going to introduce today is known as a character mining. So this is a project I started doing when I came to Emory, which was 2014. And since I was doing what Martha introduced as a parsing for over 10 years, so practically 2003 to 2000 all the way to 12. And at some point, I just didn't want to do parsing anymore, so I started doing something different. At that point, I actually really had a disinterest in the multi-party dialogue. And I kind of saw like dialogue is some kind of domain that we have to tackle. And this is the reason, because to understand the contextual information about the dialogue is very difficult, I think, to do. But yet, dialogue probably is the most important data set you can get. And here's why. So this is nothing really new to see. If you actually take a look at how the data set has been constructed, although this bottom line is a Snapchat or Twitter, which a lot of people actually think is getting increased. So this is what we call a microblogs. And there used to be a time that microblog completely dominated the social media and the data set, and this is where a lot of research came out. And it's still heavily used, especially by the US president these days. But as you can see, the increase, the size of the data is not actually increasing anymore. It has increased a lot before that. Before 2015, it was increasing like exponentially, but now it's not increasing anymore. So the next step, like the Instagram was in the exact same story, but now it started increasing again because of one reason. So it started making people to add a story about it. So it's not like a blog, but very short stories. And this is another thing that Facebook actually tried to do too. So instead of writing only a tweet, very short, it used to be only like 150 characters were allowed. But you are actually writing a story, so people are curious about like what's next coming for your life. So this is the time that Instagram started adding these features, and they now start getting more increase. So people like to hear something more than just a microblog. So and you can guess this once they're actually quadratically growing right now is this Facebook Messenger or like WhatsApp, this kind of chatting apps. So here's the thing, how often do you actually tweet or put something into the Facebook? Probably not even once a day. If you are, get a life. Most people don't. But how often do you actually put down something in your chat? Text messaging. It's like every day, it's not even every day, every hour. So the data that's actually accumulating for the dialogue is increasing much greater rate than any other kind of data. And this is the reason, and this is when I actually decided to do this character mining project, and that was the motivation behind this project. So I actually wanted to do the conversation AI as I'm doing with the Alexa Prize this year from the beginning, but back then I realized there's no such machine learning algorithm or NLP models that actually has a good understanding in the context of the dialogues. So that's why I started doing this project. The very first bottleneck of this project was we want to have a lot of conversations. But at the beginning of 2014, I asked my student to send me their text messages. And you can guess how many of them agreed to do that. So it was actually impossible to get this kind of actual conversation data. So these are type of the data that we wanted. We want to have something daily lives. We don't want to have a conversation between like travel agency to their customer. Some kind of customer service or some kind of like log from some Ubuntu customer service dialogue. We want to have a daily lives conversation and also involving possibly multiple speakers because you don't really talk to people one-on-one. You often talk to people in groups, which adds another level of a challenge to the task, but we want to have the multiple people. And also, we potentially, for a machine learning perspective, you need to have a conversation that actually carried on for a long period of time from the same group of people. So you can actually do some kind of mining. If you have a conversation with this group of people for only like 10 minutes, you won't be able to do any kind of mining. But if you have that 10 minutes happening every week for another like 10 years, probably you can do some good part of the mining. So this is why we started a project using TV shows. TV shows are actually better than movies because movies, you try to condense all the stories into 2 or 3 hours, whereas TV shows, they actually be more explicit about what they want to talk about. Lots of TV shows out there, not many of them are actually appropriate for our research, such as the most popular TV show these days is The Big Bang Theory, which is completely not the way that people talk, so we did not want that. The choice of the TV show that we made is a TV show called. How many of you actually know this show? Good? None of my first year PhD or undergrad students actually know this show, which is very, very sad. And you guys are my console people. So this is already old. The show ended 2004, and these are all old people now. But so potentially the topics and the languages they are using is not the most recent, but they are actually talking about the daily lives. They are carried on for the 10 years, and these 6 main characters actually appear throughout the entire show. So we actually decided to do the research on this. So about total of 10 seasons, there are 236 episodes and over 3,000 scenes that's available. So that's the data set we used. The long-term objective is very clear. We want to be able to understand and be able to do actual machine comprehension on it. So we want to be able to have the machine be able to answer this type of questions. And this probably is familiar to you, right? Back in 2010, I remember at Boulder, we had all our comps and groups together and watched the show together at Jeopardy. IBM Watson beating human 2 experts champions in Jeopardy all together. Actually, Martha was there too. So I wanted to actually develop something like this for the TV shows. That was the original intention of this. So originally, I planned for 10 years to have this happen. It's been 5 years. So I should be at least halfway. I got the first task towards to this introduced, which I'm going to show you later today. But we are not there yet. Answering these questions are really difficult. So, project overview. So back in 2000, so I started the project in 2015, and 2016 we introduced the first task called character identification. And the 2017 we also decided to do the emotion detection. So this is a task we try to see what's the emotion, how the emotion changed by each speaker. So this is the project also I wanted to do. And the third one is a reading comprehension. So this is given the question, given the dialogue, and you try to give out SAT or like TOEFL, GRE type of a reading comprehension question, and see how well the machine can answer these questions. And this year, we actually successfully got the working question answering model. So the Jeopardy kind of question that I showed you, so we tried our very first try of the question answering on the dialogue, and I'll show you what kind of results that we got. So all our work is available in our GitHub. So if you just type character mining, GitHub will find you for this. Today I'm gonna focus on these 2 tasks. Since these are intermediate tasks that we to develop upon to this test. So there are actually one more task I did, the personality detection too. So we try to actually see the big O type, big 5 type personality for each character. But it was actually very difficult to do that on the only text. So but we just submitted a paper to AAAI, so hopefully it will get accepted. But maybe next time I come here, I can present that work. So this character identification task is pretty interesting. Given a dialogue, and it's also a multi-party dialogue, so there are 3 speakers in this dialogue. You try to first identify what we call personal mentions. So all these mentions are referring to certain character in the show. Okay? And the eventual task is we try to map each mention to all the actual character in the show. Anybody can guess how many characters are in Friends? Including all the extra characters that appear only once. Nobody can guess. So everyone knows like these are the ones that appear pretty frequently, right? So there are about 400 characters that appear. So the task, the original task goal is to map this to any of those 400 characters. But we actually got it reduced down to only 20 characters, including the 6 main characters at the end. But and that actually covers 99% of the entire show, actually. So because all those extra characters is long tail things. So this is the actual goal. So let me actually try to explain why this is challenging compared to some of the traditional NLP tests called like Coreference Resolution. So the first challenges that we have. Let me show you. So the very first challenge is even if you actually have I, this I represents different thing in different utterances. So this is what I call heterogeneous pronouns. So if you actually think about the Wikipedia, and if you find out like Donald Trump's page, it says Donald Trump is the U.S. president of somebody. He was born in and he was the CEO of some certain company, and all this he actually refers to one person. And this is actually true for most Coreference resolution tasks. But this is almost never true for dialogue because everyone can be referring to something different. So that's actually the first challenge that we have. The second challenge is you need to link this across multiple utterances too. So the distinction between the utterance is very different from the distinction between the sentences. So sentences are still talking about very coherently and with a similar manner, but utterances, each speaker actually talks their own individual manner. And when when this person says somebody, that doesn't mean this person, right? So linking across utterance actually gives another challenge of level of challenge. So this ROS actually is all linked here and across to all the way to the top. The third one, probably the most challenging part, is the cross-document resolution. So in this context, there are 3 speakers, but this person, Ross, is talking about mom and dad, who happen to be mom and dad of Monica as well. They're brother and sister. But this mom and dad are never appear this as a speaker. So you actually have to infer somebody that does not even appear in the dialogue. So we know this mom and dad actually does appear in some other dialogues. So you need to actually bring the information from other dialogue to understand, okay, Ross's mom and dad are Judy and Jack, and try to do this kind of resolution. So this is another. The very last part, which we just introduced last year, was there are lots of plural mentions too. So I think we are actually the first group who legitimately tried to tackle the plural mentions for Coreference resolution. So in here, they actually refers to both mom and dad, which none of the existing systems actually try to link those together. So these are the challenges that we have for this task. So let me actually try to demonstrate how we tackle these problems and what the state of the project is. First, the character identification. So this is data set we created. So we downloaded, so where to get all these transcripts? The transcripts are voluntarily generated by the fans, and there are millions of fans of Friends. They are just dying to watch the show and just write the transcript for it. So we got many of those. It did take us about a half year, 1 semester, more than a semester work to clean up the data and put into the JSON format. So it is now clean structured data JSON format. And all the mentions are manually annotated, and all the entities are also manually found. So the entire annotation actually did take us about 2 years to get it done. But the data is available there, and it's probably the largest resource you can find for the dialogue part. So you can probably use it for your work. So, I was wrong. A mention can be linked to any of the 781 characters. I don't think I'm wrong, actually. It's the 781 characters total of the 10 seasons. I think if we consider only the 4 seasons, it was actually about 400, I think. So and in our experiment, each scene is considered an independent dialogue. So each episode is about 30 minutes long, and it's broken down into about 20 scenes. So each scene is is one dialogue. So mention annotation, all nominal is called a mention if it is the person name entity. So just proper nouns mostly, and some pronoun that refers to a person. And also we have a personal noun gazetteers. So all things like a brother, sister, mom, dad, teacher, all these kinds. So we try to consider all those as mentions. So this was initially done rule-based way. And rule-based way actually did really well. So F1 score of the rule-based one was about 96%, which is pretty high accuracy. We actually recently started doing this mention detection. We're using the end-to-end Coreference Resolution system, which does not give this kind of accuracy actually. So the machine learning approach was actually worse, but not much worse. It was about 94% accuracy. So these are the annotations. So majority of them are the singular mentions. It's a mention that's linked to only one entity. And there are few, about 10%, I guess. About 10% of the mentions are plural mentions. It can be linked to more than one. And these are really, really challenging problems. Entity annotation, there are 1, 2, 3, 4, 5 types of entities that we generated. So the first 2 are pretty easy. The primary are the primary main 6 characters. Those are the primary. Secondary are every other extra characters that has names. Generic is the interesting one. Generic, you actually have, so you know this is an actual person. If you look at this example, that waitress is really cute. I'm going to ask her out. Guess who said this? Joey, yes. And that waitress, a real person, it even shows in the person actually exists in the show, but you never have the name of this person. So we consider this as a generic, and these are clustered together. The general is actually a different thing. So if you look at this example, the ideal guy you look for doesn't exist. So the guy is not necessarily referring to anybody. It's a personal mention, but not referring to anybody. Those we consider as a general. It's a general term. So something like you know, that you is all general term. And other. So others are the ones that we actually know the character exists, but there's no way, contextual way, that we can actually tell who this person is from the context of the dialogue. So those are all distinguished others. So those are actual characters in the Friends. They may even have a name, but we cannot even disambiguate this. So the previous example that I showed you, mom and dad, those ones we can actually disambiguate because we know Ross's mom and dad is Jack and Judy. But these are the cases it's ambiguous enough that we couldn't even tell from the context. So if you actually read the entire season, you probably know who that person is. But given the dialogue, it was impossible. So these are the types of the entities, and this is a distribution. The primary actually consumes 67%. So majority of them. Secondary consumes 25%. Generic is very small, and 5% of general, and other is 2%. So this is the kind of entities that we do. So let me actually try to see how this can be tackled with the Coreference Resolution first. So the task that we are trying to do is we try to not thinking about the entity linking at the moment. But given the dialogue, we try to cluster the mentions together. Not necessarily we know who that is, but we want to just cluster them together. So this is a very prototypical Coreference Resolution task. But task is actually, what we are trying to do is a little bit different from the traditional ones because we are trying to handle the plural mentions as well. So we had to design a new algorithm for doing this. So there's a couple of parsing algorithms that we have to design. So the algorithm actually always compares the two mentions. One, mi, is the left mention, and mj is the right mention. So there are two mentions. And each mention, mj, is compared to all of the preceding mentions mi, which is the ones that's prior to that. So given this, it's going to be compared to every other mention. This will be compared to every other mention, so on. So it's an n-square algorithm. And these are the three labels that we are injecting for the machine learning algorithm to learn. So n means when you're comparing mi and mj, n means there's no relation. So it will just skip that relation. L means it should be mj is going to left. So mj gets assigned to whatever the cluster that mi belongs to. So you're comparing these two mentions, and mj now belongs to whatever the cluster that mi already has. If mi does not have a cluster yet, it will create a new cluster and assign both mi and mj to that cluster. So that's the left relation, because it's making the right one to the left. And the right relation actually is going the other direction. So now mi gets assigned to cluster that mj belongs to. So this is basically a flip, right? From the machine learning point of view, these conditions are exactly identical at this point. So the reason why we made these two distinctions was this. So mi and mj in this case, one that's actually having the cluster has to be a singular mention. So we are not creating any cluster for plural mentions. So if you actually found out this is a singular mention that actually will be linked to something, you will create a cluster for it. But if you have something like a mention like they, we are not creating like multiple cluster for they. We are going to create each cluster individually from the singular mentions and have this belong to they. And this is why this algorithm is distinguishing these two labels. So mi in this case will be the plural mention. So this is how algorithm works, and this is probably the first Coreference Resolution algorithm that tried to handle the plural mention in this way. So let me demonstrate how this works. So this is all the mentions from here. So Jack, Monica, Ross talking about this. So I1 is this, woman 2 is this, I3 is this, and so on. So these are all the mentions up there. And we have 2 extra mentions we add, which is a general and other. So, so it could be considered to be a general or other, so we can be compared to these 2 arbitrary clusters. So at the very beginning, there is a cluster of general and other, which is currently empty. Now, we are trying to compare I to be either general or other. And since they are not, neither of them, then the N label, no relation, will be assigned. So we'll just move on. The next one is women. So, and I read about these women. So this is a prototypical case of the general. So now this will be compared to all 3 of them. These 2 will be neither, no relation, but it will be actually having a relation with the general. So we will actually make it assigned to this general cluster. Okay. So let me go on. So this I, which is here, I thank God, which is Jack. So I here will be the same cluster as I here. Both are referring to Jack. And at this point, there's no cluster for Jack, right? So this is, since it's a left relation, we will create a new cluster and assign both of these mentioned to this cluster, generically. Next one. So ours, so this is a plural case, right? So plural, I told you, like, we cannot create a new cluster for plural. But if we already has a cluster generated, we can assign that to it. So in this case, our will be, in this case, it will be Jack and Judy, who is Jack's wife. Our it actually has a relation with the I, which is Jack, and also this I. So our can actually belong to Jack, but we don't have the cluster for Judy yet, so it doesn't do anything at the moment. So it will just pass. So one question is, if Judy doesn't ever appear in this context, it will not have a cluster, right? So, and that's okay, because there's no way we can actually tell that from the context, that our actually means Jack and Judy. So that will pass. Harmonica, which is Monica. So there's no mention of Monica before, so it will be actually, it will get passed. Ross will not be compared to anything. There's no mention of Ross, so it will also be passed. Now you, which is this part, what's going on with you? So it says actually, this is the tricky part about the Coreference Resolution. This you can be, the pronoun you can be either plural or singular, right? In this case, do you think it's a plural or singular? It has to be plural because of this 2. So we know it's plural, and we try to compare you to any mentioned before, and now it actually is Ross here. And also, there's a you, second you, which we cannot interpret from this context. So it will also get the cluster to the other. So, yes?
How do you look ahead that 2 actually is there, or do you come back to reassign it?
How do you compare these things?
So you said you is plural as well as singular, right?
You can be, the pronoun you can be either plural or singular. Yes.
So how do you look ahead that 2 exists and that's why you infer that it can
Oh, in our model, the entire context is already there, okay, right? So the embedding space will be constructed with the 2. So hopefully you learned that 2 means the plural, so it can, so yes. Okay, so given this, now you will be belonging to Ross cluster as well as the other cluster. In this case, like this. So it has a plural mentions. And similar to mom, mom is now another interesting case. So here our was actually both mom and dad, but we only had a cluster for dad, so it was belonging, it actually got assigned to Jack cluster, but it never got assigned to anything else. So at this point, we actually create a Judy cluster and try to assign mom and our both of them to.
Why didn't our get assigned to other?
Here. So that's a challenging part. So from the machine point of view, it may actually interpret that mom will never be there. Contextually disambiguate is hard. So it may just assign to this. So the system sometimes does that. In this particular example, mom and dad, Judy and Jack, they do appear a lot in other dialogues. So it doesn't make a mistake for this case. But there are some characters who didn't appear so much. It could actually make a mistake for this. So it is very possible, actually. Yeah, so especially if it didn't appear in the training data, appear only the test or data set, you will actually assign that to the other instead of mom. So, that same story, it will be same thing as all these three. So it will actually get assigned to here. So let me actually move on. So this is not, this is basically doing, guy is actually similar story, which guy is not going to be assigned to anything. So getting passed, me get to label. Let me actually pass and pass. Here you go. So this guy is the example of the generic. So look at this. Okay, I just got this from the guy next to me. He was selling a whole bunch of stuff, right? So here guy also at the same time can be assigned to other, possibly. But it actually saw it is mentioned again here. So it is not some random person, so we need to create a cluster for it. So at that point, so you anticipate not to assign to the other, but now try to make a cluster with a he. So now this generic one will be having both he and the guy. So at the end, so at the moment we actually went through everything. There's only one last step. So there's only one mentioned here that was not assigned to any clusters. So those are what we call singletons. So we collect those singletons individually, so and push to there. Some coreference resolution systems don't care about singletons because all they care about is the clustering mentions. But we actually do, because even if it is a singleton that doesn't have any other mention associated with it in this dialog, it can be linked to something else, right? And in this case, it should be linked to Monica. So for that entity linking step, we actually do care about the singletons as well. So at that point, the coreference resolution is done. So if the machine learning actually made the right prediction every time, this is the cluster that would have been generated from this algorithm. Makes sense? So the effectiveness is it handles the plural mentions quite well. And also the general and other entities are getting assigned pretty often. So now, given this is the coreference resolution parsing algorithm, now given each of the decision has to be made by machine learning, right? So during the training, we compare these two mentions, MI and MJ, and put to the machine learning algorithm, and it will give you the prediction of NLR, the three classes. So that's a classic machine learning, and we unfortunately do use deep learning for this. So this is the algorithm called, we actually introduced as an agglomerative convolutional neural network. So given the mention I and mention J, mention doesn't have to be a word. A lot of mentions that the examples that I showed is one word, but it can be multiple words. So we are actually extracting lots of n-gram convolution features from each mentions. So, and it all gets injected to one vector. So each of these n-gram features are extracted to one vector. So it's an embedding for that. These two things, and we actually have a fourth set of these kind of features. So it's not just about the mention itself. Yeah, also it's a sentence associated with it, like utterance associated with it, plus minus backward. So we have many of these n-gram features. So all these n-gram features gets embedding representation, and we have all those sets too. And for each dimension, we actually made another convolution to generate a embedding per each of these mentions too. So once you do all these convolutions, you have one vector generated, and this is what we call mention embedding. So this embedding represents MI, this embedding represents MJ. And we use lots of features to extract that part. And we also have discrete features. So there are some traditional features that people use. There are good example, easy example is like gender features. So there are some prototypical names that people use, like Mary, John. Those are gender features. So we actually include some of those generic features. So these together makes the mention embedding. These again are fused together and try to do the convolution again. So every convolution is done this way to create this one vector, which is what we call a mention pair embedding. And this mention pair embedding is now with some discrete pair features. If the pair actually agrees with each other, then put to the multi-layer perceptron using the ReLU activation, which will try to classify these three classes. So that's how exactly we learn. And this decision is used to generate that kind of clusters in the past. So this is the memory models that we use. At the moment, we are done with the Coreference Resolution. So we know how to group mentions together within the dialog, but we still don't know which entity it actually refers to. So we know a bunch of like he and he, dad is all here, but we don't know this is actually Jack. So we have to do the entity linking part. So this is the model that we used. So it's a multitask learning entity linking model. So this given, so we actually made another pass of the classification. This is per mention. Given a mention, each mention should belong to at least one cluster, right? We collect all the mentions within the cluster. And we run and as well as each mention is also compared against a lot of other mentions. So we collect all the ones who were compared that belong to the same cluster. So these are also all mention pair embeddings within the same cluster. And we made a max pool and average pool and tried to do again of the one-dimensional convolution and generate a cluster embedding and also a cluster pair embedding. So these basically represent a cluster that this mention belongs to. And this is the cluster representation also made by the mention pairs instead. So these two cluster representation. And since we are handling plural mentions as well, we can potentially have many clusters per mention. So there are like k number of clusters, we do that all together. Given the mention embedding from the previous slide, we actually try to get the average cluster for each cluster representation for the pair. And so this is a cluster representation, average cluster representation, and this is average pair cluster representation. And now it's getting all fit into the multi-layer perceptron to make a final decision. And this decision actually is the one that every dimension represents a character. And I told you like we reduce it down to about 20 characters at the end. So the dimension of this is about 20. So this is for singular mentions. We have a singular, so this is done by softmax, so whatever optimized for. But we have one extra slot that says this is a plural mention. So if it's not if this is not fired, we will try. We will trust the decision made by any of this dimension. But if this is fired, then we actually pass that to the other sigmoid layers. So this will actually do the multi-label classification. So each entity will be optimized individually, and it will be able to produce multiple labels. So this is a task that we have run. I'm doing okay, I guess. So experiments, let me show you the result. So the prototypical Coreference Resolution matrix, B cube and Ceph and Blanc. I don't think people care this metric so much, so let me explain a little bit about B cube. So CCC, this is the paper that we actually published to Connell 2017. So that was the previous state-of-the-art approach that we didn't really handle the plural nouns. So if you actually don't handle the plural nouns, all this stuff, this approach actually was doing about 70% accuracy on the, and Coreference Resolution 70% is actually not bad. You guys actually have to understand. But with our new approach, we can handle both plural and singular noun, and we got up to the 74% for the BQ score. Entity linking score is actually pretty much lower. So if you actually take a look at only the singular mentions, F1 score is about, so from the previous approach and our current approach, singular mention scores are about the same, because previous approach actually did well for the singular. It's when the plural mention, it was doing noticeably worse, 29, 30%, and about 41. And if you think about the 41% F1 score, it's all still pretty bad. It's still, I guess the random chance is 1 out of 20, so it's better than that, but the accuracy for the plural mention is still very difficult. Overall, the overall accuracy for the entity linking is about 67%. So that's what we're getting. So if you actually are curious about the character-wise entity linking, so the first 6 characters are the main characters. And if you think about the, look at the entity result, they're actually pretty good. If you consider only the singular mentions, they're above 80% on average, which is actually, so this means in any dialogue in Friends, if you actually run this tool for the main characters, you can reliably find the main characters like in 80% kind of accuracy. So it's actually pretty good. But all the other ones that actually appear only like 1% of the data, it doesn't really do that well. So.
How good are people at this?
Sorry? How good people do this? So I don't actually have the number for the plural. But singular, I think it was actually doing about low 80, low 90 or high 80. That was the number that we did. Yeah, so people, human actually does better. I think I didn't put that number in the paper because I think our evaluation was biased. The people who actually evaluated this as a human, they know the show very well. So they don't really need to even look at the text to know this stuff. So that's why I don't think that number was actually legit. But okay, so these are the character identification tests that we have tackled. And I think this is a very fundamental test that has to be solved in order to understand the dialogue context well. So given this work, now the very latest approach that we did was the question answering. So let me try to introduce this a little bit. Let me try to make this in 5 minutes. If you're not familiar with the question answering task in NLP, there are mainly 3 types of question answering tests that people run. So one is the reading comprehension, which we actually have done before too. So given this kind of text, then you actually try to ask a question like, what's the name of the troublemaking turtle? And James, the turtle, so we all know the name, but it will actually give you the multiple choice. And it'll give the multiple choice and try to see, and the multiple choice is giving out, this is not even reasonable, right? James and Jane, maybe reasonable. Freezer, seriously. Splinter, I don't know. So anyway, this is a reading comprehension task. And the second kind of test is the closed style QA, which is also pretty fascinating. So this is given a news article like this. You try to have the description about the event happening in the news article and make the one blank and make the machine actually guess out of this context. And it actually has to guess the person name. So this is the closed style QA. Closed style QA can be also tackled by multiple choice kind of thing. Because if you actually know you're always asked for the person, then you can run the name entity recognizer, extract all the persons first, and try to pick one of the persons. So that can be done. The test that we are trying to run is a spam-based. So this is probably the most popular form if you know the QA dataset called like squad kind of dataset. Given a context, we actually have the question, and you're supposed to find the answer from the answer span from the context. So this is the task that we are trying to do in the FriendsQA. The major challenge in this task is the evidence task is the multi-party dialogue. So this actually makes a whole lot of difference. So if you think about these kind of cases, the context from Wikipedia is very similar in a way that is written for the question, right? It's both written in some formal descriptive way, but in the dialogue, you may not actually even complete your sentence. So if you're talking about like a birthday cake, somebody started like, hey, and second say, what's up? I got something for you. What do you have? I have a cake. What is for? It's for a birthday. And if the question is like, what did Mary buy John? So you will never say birthday cake, right? Because those are like scattered, the information is all scattered around. So unless you understand the entire context, you cannot really answer these kind of questions. Whereas this kind of setting, you can more or less do some kind of string matching to get the answers out. So that's where the challenge comes. Let me elaborate a little bit more. So entity resolution, which we actually look at in the character identification task, is a very difficult thing to do. So if you actually read this context and say, who forced Rachel to raise the stake? Who is it? Monica, yes. You know, in which season? If you know the season, then you have a life like I do. So, so it's a Monica, and take a look at this. Here, she forced me. It says that. So first, you actually have to know who she is. So hypothetically, we could do this with the Monica by using our previous task, and raise the stake is written here, right? So no one forced you to raise the stake, right? So you need to know who you is, and you actually have to understand this part compared to this part. And the meaning of that is not true. Because here somebody says no one forced you, but here she's saying somebody forced you, and that somebody is she. You see why this task is difficult, right? So this is what's actually happening in our data set. So I actually got the real examples. So you need to handle all this kind of situation. These are obviously classic examples of NLP. It's not necessarily for dialogue, but we actually have a lot more of this because we are handling TV show, which are supposed to be funny, and people try to be intelligently funny like Chandler, and use lots of metaphors and sarcasm. And so it's look at this. Hey, Joey, what would you do if you're omnipotent? Probably kill myself, excuse me? And little Joey said, very funny example, right? That's probably the only reason why this paper was accepted. So why would Joey want to kill himself? To do this, you actually have to do the inference of understanding omnipotent. Joey understood it as I'm impotent. And this means little Joey is dead. That's probably why Joey wants to kill himself. No deep learning will give you that. Just no way. So difficult, happen a lot. Sarcasm, the big one person who makes basically 50% of his speech is sarcasm. Morning, to say morning, hey, you made a pancake. Yeah, like there's any way I could ever do that. Did Chandler make a pancake? Yes. The machine will say yes, right? Because he said yeah. But we all know it's not. So this is the challenge part about this dialogue. So let me go into the type of questions, the real examples that these are one dialogue that we pull out from our data set. And these are types of questions that we try to generate. So it's the 5W1H questions, which are prototypical, known as a factoid questions. But this is actually pretty difficult. So this is what is Joey going to do with the KC tonight? There are more than one places that it says about it. Where are Joey and Chandler? Central Park. Who is Joey getting a phone number from? It's Casey. So if you actually notice this problem, who is Joey getting a phone number from? We actually annotated only this, not the later Casey. Because we want the machine to learn this is actually the context that actually should get the answer from, not some other parts. Just because Casey appears a lot, we don't want you to pick it. So we actually try to. So, and obviously what do you think is the most difficult questions? These two questions, right? Those are long answer questions. So those accuracies are really, really low. So let me actually try to finish in 2 minutes so you can actually talk something. So answer span, we have some rules for answer spans. This is some conventions we made for the annotation guideline. So, and we did lots of crowdsourcing. At the end, our annotation quality is actually pretty good. It's about, after we did all the cleanup and the pruning, it's above 80%. At the end, we actually made it to high 80, which is very acceptable kind of quality. So data quality is pretty good. Over the summer, we actually even cleaned up more. So we used the same first 4 seasons of Friends, created all these answer data sets, and we did a lot of analysis, but let me skip this. So you guys ask me questions. I think I'm running out of time. So we ran this into the 3 state-of-the-art question answer systems out there, including the latest approach, BERT. I think BERT is now obsolete. It's been out only for 6 months, and it's already obsolete. If you're in machine learning related computer science field, too bad. Your state-of-the-art will not last for 2 months. So when I was PhD, when I established state-of-the-art, used to last about a year. Now it doesn't last for two months. So experimental result, there are many different ways. At the end, the best result that we got for the spam matching is about 64%. Compared to the Wikipedia question answering squads that we showed, I think people are getting up to 90%. So, but since it's much more challenging question, and I think our data set is also smaller than squads, so it's we currently have we have something better than this, trying to submit to ACL about 67%, but it's still very low accuracy. So we did error analysis. Many different types of errors comes out. These are the overview of the character mining. I'll be happy to talk about it after. I'll be staying here until 5, so please do. One thing that I do want to show academic trees, two familiar faces you probably know. Have me. They are not father and mother, but they are more or less. And produce a lot more students since I came to Emory. So I am hoping this will happen to all of you. And really happy to be at CU. Thank you.
So we have a few minutes for questions.
Can you apply this to novels as well?
Novels. Yes, I think so. Novel may be actually even easier because it's more Korean and there's more narratives that's coming out. But yes, I think people actually try to do novels for the reading comprehension and also closed style. I don't think there's a work for the spam based, but I don't imagine it cannot be done. So novel maybe I thought about doing the children's book.
Yeah.
So that's the domain I originally thought about, but I wanted to move on to the dialogue. So yeah, I believe so. Yes.
And another thing, can you do is there scope for relationship extraction between the characters? Like you could know.
Right.
Yeah, what's the relationship between Monica and Sandra? Are they married or are they roommates?
Right. So that's the eventual goal that eventually we want to actually build a big knowledge graph out of all these characters and match that to some metadata that we have. And so at the moment, we are not there yet. The character identification is not as good as the stage is being. And there's also another level of semantic parsing involved. So which we are actually working on currently, but it will take another couple of years probably to get there. Yes.
Because your model has been trained on scripted language,
Mm-hmm.
do you think it could be problematic if you try to use it on real language?
So there are one or two. So this model may not actually work for all domains. For example, the one that question answering model actually can work, but the character identification model, when we try to apply that to the Big Bang Theory, obviously doesn't work that well. So, but the question answer model I think is actually pretty good. The script language is actually harder than the real conversation. So because of all the reasons that I was showing, like the sarcasm and metaphors, they intentionally use that so much, and also humor, which we don't do so much as much. So actual conversation, there's a difficulty level of the discourse. So the sentences are not well organized possibly, but other than that, scripted languages are actually harder to do. So this Coreference Resolution tool, we are actually currently trying to use that for our the Alexa Prize project. And it's been working okay, not the best, but it's been working okay. So, Any other questions?
Well, we're pretty much at our
4:30.
4:30, yeah. So there's cookies and coffee and lemonade up here, and Jinho will be here for another 20 or 30 minutes or so. If anybody wants to follow up with some more questions one-on-one or ask other questions about Emora, we'd be happy to talk to you. So thank you very much.
Thank you.